啊？不会的，考给他看。哎，不能，如果你非要 NE 的话，你还是要买。那这边你没有拿哦，只要一门一点气就 OK 了。OK， 袁景，你加油，可以的，可以的，区数学吧。可以。Okay, how's your preparation, Mika? How's your preparation? 哎，你们今晚还有2补吗？啊，已经几天没有睡了。
3天。
哎，你们可以约个 revision 的，你们可以约一下。来招生那边可以约一下。
你们那有来吗？
组团，你们在一起有就来啊。你们呢？你们分开我就很难来啊，我要去这边要去那边，在一起啊你们。啊 ，OK， 休息的时候谈那点。OK， 上课。OK，let's start first 啊 ，let's continue 啊。所以 OK 啦，可以的，可以的啦，哪里不可以？是不是你骗他平时 ？OK， 来 ，let's start first。Okay, so let's consider two topological space。哇，有零食啊？对的。哦，等一下，Okay, let's consider two topological space。哦，那个。So if we consider two homomorphism between two topological spaces, actually, what is true is if you just throw away one point, okay, from each set here, okay, this H will remain a homeomorphism. Okay, last time when we construct continuous function, right, we said that if we restrict domain or restrict codomain, it's still continuous, right? But in this case, this homeomorphism is preserved under removing one point. Okay, what is homeomorphism again? What's homeomorphism? 这什么？问你啊，问你啊，什么 ？homeomorphism 啊，一种 continuous function， 怎样的 continuous function？ 啊，怎样的？啊 ，function 有什么 property 啊？很好的 property 啊，有两个很好的 property。injective 还有 surjective 哦 ，OK， bijective continuous function。But homeomorphism is more than that， 还多一个，它的 inverse 也要 continuous。OK， 它是 continuous function 有 inverse， 它的 inverse 也要 continuous。OK， but 什么啊 ？but okay, never mind. Okay. So let's do this. Okay, first thing is if you restrict your H, okay, to this punctured. Okay, let's call this punctured X here. Yeah, I remove one point here, punctured. It is still bijective. Okay, it's still bijective here. Okay, because it's bijection on A, right? But the two domain and codomain element are revoked together. The others still bijective. Okay. Then what's left to show is we want to show it is a homeomorphism. Okay, inverse and F is still actually still continuous. So meaning what? We show that U is open, X punctured, if and only if hash U is open in Y punctured. Okay, so note that in Y we are puncturing the image of A, sorry, A or X. Punctured 懂吗？大家 punctured 啊？punctured 啦，马来文 punctured 啊，英文是 punctured。哦，中文是中文是可以几块，爆胎好爆胎呀，爆胎，背刺，是 punctured，打洞，OK 呀，OK 有力动，OK punctured。Okay, so two direction. Okay, let's do one direction first. So suppose U is open in X, take away a point A. Okay, so note that U should be U intercept X, take away A. Okay, maybe this is trivial, but this would be helpful when we compute FU. Okay, so we want to show that FU is open. Sorry, HU is open. HU is open in where? So what's our goal here? Our goal is HU is open in the punctured codomain. Okay, so what you do is you show that it is open in this subspace topology. Okay, also HU can be written as HU intercept this punctured codomain here. Okay, but I think the proof is quite trivial. So if you write HU, right, you can write it as HU intercept the whole set here. So this is a demonstrate how useful is set theory. Yeah. Very trivial. I don't need to copy. You just have a read. And then hash on intersection is what? Hash U intercept hash of everything here. Hash on complement is what? Here is again hash X take away hash A. But hash is bijective, right? Okay, so basically hash X is just Y. Okay, so you recover that hash U actually is the intersection of hash U with the okay, nothing special here. It's just a bunch of set theory. Yeah. The other direction is the same. Quite straightforward here. But non-straightforward things from here is this example here. Okay, this one, the other directions would be similar. Okay, but you use the inverse part, this image. Got question or not? Okay. Is it okay? Question? Just applying set theory. Okay. Okay. Come on. Yeah. You think there's only one inclusion? Which part here? This part. You sure? So let's check. Maybe it's a good exercise for you. It's true. Hey, where's my function thing? Yeah. Oh, right. So intersection only for one direction. Huh? It's inclusion. Okay, let's check. So can we really split them up or not? Let's think about it. Hmm. So can we really split it up? Okay, so let's write down first. You're saying why?
Actually, you can ask.
Okay, why?
Because
Mm.
we know that H is bijective, so we can treat H as the pre-image of the inverse.
So
Pre-imaging can just
okay, so how should we write it better? Oh, if equal is F is injective. Okay, so the point here, maybe put lemma here. The quality false is H is injective. Can you briefly say why? Why? Definitely we have F injective because subjective. So why injective imply this? Why you go the other direction? So the other direction says what? If you have two elements in this intersection, right, it comes from something in the intersection. If you are in the intersection of images, it comes from something in the intersection of pre-image.
can change you into another application because
Why? Why is it confusing?
also first you use a whole set index minus play, but the second you actually try to get a whole set minus.
Oh, U is open in this set here. There. But U is inside X. Correct, but I already assume that it's open. But this intersection is just saying that U is inside X minus A, right?
Right, this intersection try to mean substrate topology, right? So I think
Let me think. Should we talk about subspace topology here? So we show that U is open in this set if only if the U is open in this set. So what do we need to do to show this statement here? I want to show that U is open in this set if only if the U is open in the other set. So how is it U open in X take away XA here? So we try to use subspace topology. Okay, actually, correct. I think you are correct. But I'm trying to play cheap here. So no matter how you run, I guess we can just consider U as this type of U. Why do we do this? How to justify this? Okay, so let's say follow your step. Let's say follow your step. So so let's follow your step then. So let's say you got a V, right? So there's a V open in X, and then you can write it like that. Then hash U is just hash V on that thing, and then everything is V. But because hash, huh? Yes. Right. So actually it's not equal lah. So maybe we would like to say without laws of generality, just take f take u equals to, well, I mean, okay. So from this story, what we see here, okay, what we see here is this v is like a placeholder for an open set. So if you just put it as u, it doesn't matter. But morally, you cannot do that. Okay, let's do v lah. So morally, we must be morally good. Huh? Morally is by law. We should work by law. But we don't go scale. By law, we should take a v from v open in X. Okay, because if you look at this argument, right, what is v doesn't really matter. What's matter is hash of that thing should be open. But hash of that thing is open because hash is a homeomorphism on X. Yeah. Okay. Have we solved the problem of equality here? Huh? How to solve this problem? Why equal? When is it equal? What's our contradiction last time? That's the do I give you contradiction? Other example, yeah. So non-injective one. So you guess that it should be injective lah, so that you won't get this problem here. Okay. So how this one no bracket. Can we show it? I think this is a midterm question, so you can think about it. So if you have this only this inclusion, right? How about go backward? We know that our page is injective. Can we go backward? Okay. Let me write down a simple statement here. So if hash is injective, is it true that hash A intercept B contain hash A intercept hash B? Okay, think about this. Hey, I think this one is obvious or not? If you are hey, why okay, sorry. Okay. Really you think injective, correct. Okay, let's prove this. Okay, I'll prove this. Okay, prove this. Okay, suppose y lah, just use y because it's the image. Living in hash A intersect hash B, right? Okay, this means what? This one really midterm like question. You should be able to write this. Then y is in hash A and y is in hash B. 没有废话，很重要哦。这个从这个 cat 变到 n 是很重要的一件事情。Okay, because you turn from set theory to propositional logic already. Okay, next step, So there exists some A in A and there exists some B in B such that y equals to hash A and at the same time y equals to hash B. But hash is injective. So hence A equals to B, but A is in A, B is in B. So A and B live in intercept B. So both of them live in intercept B. Okay, good. Okay, can follow? Okay, yeah. Okay, very good. Thank you for pointing out this technicality here. Pretty important. Okay, the other direction is similar, so you could try it out. Okay, one non-trivial implication from here is this guy here. Okay, for example, we could show that the closed interval 0 to 1 is never the same as the open interval 0 to 1. Last time we said that what these two intervals should have the same amount of elements. Okay, 一样多, but they are not homeomorphic. Meaning what? So there's no function that bring you from one open set to the other open set and then come back. Then you cannot go forward and then not jump across. You can go forward maybe, but you cannot come back. Sorry? Yeah, I skipped the other direction. Oh, yes, I skip it. Yes, similar. Yes, I skipped the other direction. It's similar. You can try it out. Okay, so how to prove this? So if you want to show that there is none, right? So suppose there is. Okay, suppose there is one for contradiction. Okay, suppose there's a homeomorphism. H close interval to the open interval. Okay, so what is inspired by the previous theorem is if you remove one point, okay, it still remains as a homeomorphism. Okay, so there's a very clever one point you can remove here. Okay, where's the clever one point? Either 0 or 1. Okay, let's throw those. So if I remove, okay, let's follow 1000. 0 to 1 from closing the 0 to 1. What happened to this H1 here? H1 here must live inside the codomain, right? Any point from 0 to 1, but not 0 or 1, because there's no 0 1 here. But by previous theorem, what did you see? If I restrict this H, right, to just this half open interval here, okay, I should get a homomorphism between the punctured codomain as well. Yeah, I punched at H1. It's still a homomorphism. Did you see a problem here? Hey, sorry, confused. ChatGPT go wrong. H0. Okay. So what's the problem here? If this is still a homeomorphism. Is it about injection? What happened to this image? Split. Split mean what? Not connected. But H is homeomorphism. It's continuous. The domain connected. Continuous image of connected domain should be connected. Okay, but now you can't disconnect them. You have a separation already. Okay, so but now the image of H is not connected. Okay, so contradiction here. Okay or not? Okay, so closed interval and open interval is never homeomorphic. But if you think about it, if I remove any point from 0 and 1, right, then you won't have this argument valid already. Okay, because you might have a image of discontinuous set. Then disconnected. Okay, so this motivates the following definition here. Okay, so suppose X is a connected topological space. An element A in X is called a cut point. Okay, cut point if X take away the singleton set A is not connected. Otherwise, X is a non-cut point. Okay, non-cut point meaning even if you remove it, your set is still connected. B. Yes, thank you. Should be A. So a subset A in X such that X minus A is not connected, they will form a set called cut set. So if you collect all the cut point together. In particular, this cut point stuff, I think it's really important for your complex analysis. Okay, because you want to talk about simply connected domain. Okay. How to think about this cut point? I don't know in your kindergarten, kindergarten school, did you play something like there's a say cut paper, cutted paper, so that you can tear it, and then you got the shape. 我记得不算折纸，就是它好像有打洞过那种很小的洞，然后你可以沿着那个洞撕，或者沿着那个洞剪。哎，不懂我在讲什么？怎么？啊？怎么可能？比如 like let's say like 画这样嘛，对不对？这样嘛 ，maybe something like that。然后你就沿着它剪嘛。
OK，
有吗？不是有诶，对不对？有些已经是来你可以直接撕了，对不对？啊，yeah. So they make the cut set for you. These are all the cut set. So all the point here are cut point. 对，你看一下它就断了。对对对，就给你容易撕。邮票也是，邮票，that's right，邮票，So you make，因为邮票就是你从一个大张撕下来。Okay, so those side are the cut set or all those points called cut point. Okay, good. Okay, very good. Okay, so let's see what are the example here. Okay, so how about this example? Okay. Right, so let's look at this familiar example here. I think all of you look at the same lecture notes, right? Or Tao Seng use different lecture notes. Use different shape. I think this is the calculus 2 rows. Okay, R equals to cos 2 theta. Okay. Can you imagine where is the cut point? You want to cut such that this set is connected. Where can you cut it? Can I cut it somewhere here or not? Is it still connected? Not enough, right? So other parts still connected, right? So where can you cut it such that this set is not connected? Yes, the origin. Okay, you can take away the origin such that it's not connected. Okay. 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 So this is a cut point here. So let me label here. This cut. Okay. Actually, in my notes, I show that all the leaf take away this cut point is connected. Okay, you can try and show it as well. Okay, how to show it? You can show it by it is a continuous image of a connected set. So meaning what? You actually can parameterize this leaf here. Okay, parameterize this leaf here using an interval. And then you're good. Okay, but let's not do that in class. Okay, let's go to the next part. So there are a few nice lemma about connectedness and subspace. So first thing is if C and D, or CD forms separation of X. And if Y is a connected subspace X, then a Y lies entirely within either C or D. Okay, so can you imagine what this says or not? Okay, if you got an X, right? Okay, and then you got a separation C and D. Okay, if your Y is connected, it cannot stay half, or it cannot stay half here, half there. It must either live on the left or the right. Why? Because the separation is supposed to be empty, right? Intersection. Okay, so nothing should live in the intersection if this set is connected. So I should live either in C or either. Hey, this is like how your brain works, you know. Your left and right brain. Actually, it's not connected. Okay, but it is connected at something else. But the left and right brain is like not matched together. 知道什么意思吗？你懂我讲什么意思吗？ Like 听我讲 ，okay, maybe 是这个表达一点。So your left and right brain, right, is not joined together. It's a left and right, but they are joined using some maybe chip in the middle. But 什么？屁股？
有屁股啊！
如果屁股接起来会怎样？会大便。
这才讲大便哦。
But my point is, if your brain, right, okay, if you're connected, like the part that work on the left brain or the right brain, go to a middle how, then your brain got confused. Become genius. Or maybe on one spectrum you become genius. On the other spectrum you become what? Mental problem. Okay, so yeah. Okay, so make sure you lie on the right brain. Use the right brain. Yeah, you're confused. Okay, you'll get confused. Okay, so how to show this? Okay, let's see how to show this. Okay, let's see how to show this. So proof. Suppose if it is not the case. Okay, suppose it is not the case. So meaning that some part lie inside C, there's some part lie inside D. Okay, but this means what? If it is not the case, you write some part in C, some part in D. This means what? Such that actually this form a separation. Okay, for your Y. Okay, actually this will form a separation for your Y already. So okay, test you. What do you need to check? Okay, to check that this is a separation. How many things you need to check? 3 condition, right? So first is what? This, okay, disjoin first. Disjoin, non-empty, open. Okay, usually we will show non-empty first because if empty, you don't need to disjoin anymore. So let's do non-empty first. But this one is by assumption because let's say we assume can split it, right? So this one is by assumption. But why is it disjoint? Because we know that C and D is already disjoint. Okay, because we know that C and D is already disjoint. Open obviously open. This is open in the subspace topology. Open at subspace topology. Okay, so you will produce separation. Okay, very simple argument, but please don't forget it. Please don't forget it. Okay, the other lemma, very interesting about connectedness here. Another lemma is, if you take a bunch of connected subspace together, okay, all these subspace are themselves connected, but let's say they share a points in common. Okay, actually the whole union is connected. 什么意思啊？你要两组人哦在一起，不是？你只要有一个人躲在里面就好，同一个人躲在那里，这两组人就会 connect。Okay. Okay. So let's prove this. Let's prove this. Let A alpha be a collection of connected subspaces of X. Okay. And then we found the common point here, P. So let P in the intersection of A alpha. And then we want to show that let's call it Y, the union of A alpha is actually connected. Again, showing something is connected is hard. You have to show no separation. So what do? Suppose for contradiction. Okay, so let's suppose for Seng contradiction that Y can be written as C union. So disjoint non-empty and common. Okay. Hey, note that here the CD here we didn't say that they are proper, but they should be proper. They should be proper. Okay. We don't need to include the proper condition, but it should be proper. Why? Otherwise, the intersection couldn't be disjoint, right? But it must be proper. Because why I mentioned this? Because if we learn the irreducibility property, right, we need the set to be proper. Because there we don't have disjoint property. Because if you can write as a union of yourself, then what's the point? No point. Okay. But for irreducibility, okay, it's not for this class, maybe for AG. I want to mention a bit. For irreducibility, right, you could have proper closed set, but the intersection could be non-empty. But connectedness, we want disjoint. So that disconnect. Okay. But irreducibility doesn't matter. Okay, as long as you can write as a proper set. Union of proper set. Okay, so since this is a separation, right? So you could ask a question, where P have to be? P is a point inside the intersection. Obviously, it's in the union. Okay, but this is a separation, right? Okay, so where should this P live in? Because these two said the intersection is disjoint. You cannot say that the P live in the intersection. Okay, so it must live in either one of them. Okay, so suppose so without loss of generality, yeah, I think can. So without loss of generality, let's assume that when someone call me. Ya, 9 pagi, right? Saya akan bertanya. Oh, dari tempat. Dari tempat. Oh, saya boleh. Sabtu dapat Sabtu siapa yang pakai tidak menolak. Okay, hello. So without law of generality, let's suppose that this point live in C. Okay, so what can we say here? So note that A alpha is connected. And so just now, what we have proven, if you have a connected subspace, okay, your left and right brain, right? So it must live either in the left brain or the right brain in the separation. Okay, so meaning A alpha here, okay, A alpha here must either lie entirely in either C or D. Okay, so what's the fields here? So let's draw the picture again. So you got Y, okay, you got CD, okay, you got a point. So, well, I mean, you got how to draw. You got a lot of A alpha inside here, right? So you got a lot of AF alpha here. Maybe because they are intersect at one point, right? Okay, let's call this point P. But we said that P is in C, right? So let's move this flower left a bit. Because we said that, okay, let's assume that the intersection is the middle point, E. So this is a bouquet of flower here. We have bouquet of flowers here. So there's a point in the middle P. We assume that this P is living in C. Okay. But these A alpha are connected. If you look at each A alpha, it's connected. Then A alpha got the point. Every A alpha got this point P live inside C. Meaning what? Every A alpha must also live inside C. Okay, so slowly, actually, everything should go into C. Okay, so actually, there's nothing. Since P is in C, there's no A alpha could live in D. Huh? So, where's the contradiction here? Where's the contradiction? 啊，懂吗？还有东西吗？D 里面还有东西啊？没有 ，but D become empty 了。Just now we said that C and D must be non-empty. Okay, so therefore D is empty. So a contradiction. Okay. Okay. All right. Okay. So the next step. So in this case here, what can you see here? What we can see is there's an equivalence relation here. So if A is in a topological space, we actually can define the largest connected set containing largest connected set containing A. Hey, this one sounds very familiar. Assignment. So which assignment is this? Yes, so you found I remember again, right? Maximum what? Maximum open set, maximum open interval containing A. So how do you form this largest connected component here? Exactly the same construction you have. So you just take the union, okay, union of all connected set in S containing A. Okay. In this case, we will call it a connected component of A. Okay, so finally, we define this definition, connected component. Okay, it's the largest connected set. How do we define this largest connected set here? We use union of all the connected sets. Okay. So one thing you want to check is maybe we don't check here lah. One thing you should check is these connected component form a partition of your topological space. Okay, in particular, it defines an equivalence relation. Okay, right. So we have a bigger theorem here. There's a bigger theorem here. So a bigger theorem here is a homeomorphism must map connected component to connected component. So just now, previously, we just show you that continuous function, continuous image on a connected set is connected. But now, if you are homeomorphism, okay, you will send a connected component to connected component, no matter how you adjust it. Okay. So if it's sending a connected component to connected component, meaning what? You will have a bijection of this connected component. Okay. So meaning if left hand side got this many of connected component, right hand side also need to have this many of connected component. Okay. I'm not just counting the element inside this set, but you also preserve the connected structure. Okay, connectedness here. Not just bijective on elements, but also how you view these points together. Okay, inside this topology. Okay, let's not prove these are quite tedious. Not tedious, just routine check. But let's look at one example from here. Look at this example here. Look at these two stuff again. Again, it's the roses. Today gonna be very romantic. Oh, sorry. 现在是要安排520这样对吧 Okay, the first one is the r sine 3 theta. Next one is r equals to sine 2 pi. Okay, let's think about this. Why is this not homeomorphic? 对对称，好，我符合你的 PDST。喂，不要这样坏，不叫 PDST 啊，叫什么啊 ？PDST 是啊 ？OCD，sorry OCD。PDST 是什么啊？什么症候群啊？OK。OCD。哎呀，不要嫌这样多啊。OK， 来。So why these two are not homeomorphic? Let's think about it. Why is it not? Zero. What do you mean zero? What?
So at the left graph, there's 3 thetas in R0, right?
Okay.
And there's 4 thetas in R2.
There's something to do with the number 3 and 4, but it's not about 0. Not about 0.
Which means that line 3 data has 3 connected components, but line 2 data has 4
connected component. But previously we say what? It must sense connected component to connected component. Okay. So what's the full argument here? Suppose there is a homeomorphism first. Then after you remove the cut point, it's still homeomorphic. So meaning what? If you really want to take away the same point, right, you need to produce a homeomorphism that send this origin to the other origin. The claim is you can do it. Did I write it down or not? Let me see. Yeah, I didn't, but you should be able to do it. Okay, no, and but after removing it, still homeomorphic, right? So homomorphism send connected component to connected component, but one side got 3, the other side got 4. Okay. But let's say maybe your homeomorphism cannot send to this point, huh? Could be other points, man. Let's say if you send to other points, what happens? How many connected components will have? Huh? One connected component also doesn't match with 3. Okay, so either you get 4 or you get 1 connected component set. Okay, yeah. So it's not 3. Okay. Let's see. All right. Let's look at the next one. And what time is it? Can we prove the last one? Let's prove. No. Huh? Break. Oh, that's okay. Okay, let's break until 4:09.
Yeah. 给你狡辩。要啊。
是吗？都有控制，那个点
多少吗？
第三天没送，做了2本去过了。
第三个开播我改了，
你看到了，看到了。但是我还没送第三题呢，我没有看。第一题那个 lemma 是不是可以用 Gauss lemma 来做？
第一题
的那个 lemma，
好像我看到的是没有吧？
它的第一题说白了就是说，让你用一个 lemma 去证一个 tier， 然后再用你这个 tier 就做到题。
我不会直接这样写。刚刚哪一个？应该是那个有一个 P 的那个，这个有 P 的吧？我就讲 P 在一个 point 在这边 ，P 也 point 在这边，然后我就讲，因为它的 Y 因为这两个 disjoint，所以它只能在 C 或者，可是 P 是一个 common point，所以它在两边。然后它就 contradict 那个，所以可以再玩。
我看一下什么？你说P 一定在 C
或 D 的其中一个，但不能在两个。
对，然后
所以可是它是 common point 嘛，所以就要在两个都在嘛。
可是它 common 是 A alpha common point 啊。
什么是 A alpha common point？
就是说 A alpha 的 intersection 啊。可是你不是很懂这个 C 跟 D 怎么分这个 A alpha 对不对？你的 C 跟 D 只能够分 Y 罢了。你现在能用的东西是这整个东西在 Y 里面，还有 P 在 Y 里面，就这样吧。什么？没有，你怎样用 P 又躲在 D 里面？
没有 P 只能躲在 C 或 D 的其中一个嘛。
OK 啊，对。
因为可是如果说P 躲在 C 或 D 的其中一个，就跟 common 这个字就本身就已经封锁了。
没有，这个 common 是 common of A alpha， 不是 common of C 跟 D。
讲 common of A alpha， 还有 common of Y。
是每一个 A alpha 都有这个点，
对，
所以他们 intersection 一定要有这个点。
哦，
它是 common to A alpha， 不是 common to C 跟 D， 而且不可能 common to C 跟 D， 因为 C 跟 D 本来 assume 就是 MD， 所以它只能活在其中一个地方的。
它一直都只能完全一个。
因为你活在两个地方，你就 contradict 这句话。
呀，好，再看一个。
没有，那个 common 是 common to 谁，你要搞清楚。
哦，
那个是 common to A alpha。
我可以拿一个，可以拿一个。
想做，想做 A，
干嘛？
在考试。
考先咯。
应该只有第一题比较难，第二题应该比较难。第三题我不知道。
第三题可能想有点难，但是写出来应该不会太难。
啊？第三题。
如果你有一个 variety 吧，然后你 project 去后面 n 减 l 个，就会等于你去拿那个你原本的那个 idea 去 intercept 最后 n 减 l 个 coordinate generate 的 idea， 感觉很合理。
我觉得条文
啊。
你的三问和其他老师看到差一点。看你的三问，看阿拉斯。
你的三个做的太累了，
阿拉斯看两话，
就是基本上不可能靠独立完成，你知道吗？
看你的，2天也写不完。
对啊，你的至少我得查很多，像我刚刚那个，你知道为什么我会用高斯莱玛吗？因为那是我查出来唯一一个我能 proof 的 proof， 而且网上没有完整的 proof， 你知道吗？是我把两个 proof 两个帖子上面的东西给点拼起来。
我那时候，
等下我在这边给你看，其实不要用那个。
不会，我用那个只是因为我读得懂而已。
可以，我觉得很，就讲究不同的。
我的想法就是因为它，我跟你讲讲我的高斯莱玛怎么用好不好？就如果 F 和 G 不是它本来是那个叫 have no common divisor in KXY， 然后用高斯莱玛可以说明它 has no common divisor in K 圆括号 X 和 Y。
他们一开始就没有那么。
对啊，这只是因 KXY 方括号而已，我把它放到在 K 圆括号 X 方括号 Y 里面。因为
不要这样严谨，
因为 K 圆括号 X 是 field of fraction of KX。
啊，要讨论到那边那个世界去。
我是用那个做的。
OK，
因为你用了那个以后，就在那个世界里面，因为它们没有 common divisor， 所以就可以把一写成
因为
linear combination。
也没有用到底的。
有啊，因为你把一写成了那个 UF 加 VG， 然后把 U 和 V 的 denominator 消掉，变成了 W 等于 WUF 加上 WVT。然后这个 W 是一个 KX， 因为这个 W 是活在 K
在我们班上做，
所以它的那个 root 是有限的，所以得出来我的 A 的选取是有限的。然后同样的做法，我可以得出 B 的选取也是有限的，所以它的整个是有限的。
OK，
是不是很好玩一局？
不错，可以啊。
我觉得这个题最难的是 prove 你那个 lemma， 有了 lemma 去 prove theorem 就简单了，有了 theorem 去 prove 那个题就简单了。
OK，
至少我做下来感受是。
他们开始做呀。
第二题超简单，超趣味。
一点我知道。
觉得这个第二题出的太趣味点了，你把这两个题放在一起，它的对比感很鲜明。
厉害。
不是，哎，就那个你的第一题和第二题。
Red，
那个 red。
FN
这整个题就很趣味，你知道吗？跟那个第一题放起来，这个对比感真的是吓死我了。
可是你们很少看过这种题目吧？这种 classification，
因为我就是
我有看过这种，
就是这个 specific 的 classification 很难，我觉得。
有题不讲 FN 在 J， 还是 FN 要在 Red J 的
FM 这种。
也 FN 在 J， 然后 FN 在 Red J。
这是 red 的 definition 啊。equivalent definition of red。equivalent definition of red。对，OK 啊？什么？有没有好更哈？
我觉得这很好。
有的好更，因为你有2个方向要顾， 因为我们的 definition 是 red eye。所以有两边，一边应该是蛮 obvious 的，另外一边就是在上头。
And you like some the
严重算不了。哦，我刚才就看到了。也是不都不是那个元素的，还有那个你哎呀，好多啊，然后好，还在写，
觉得你的那个地方
写起来应该没有很长，但是不知道
跟第一次
啊会比较短，会短，
会比较简单。
我不知道简不简单吧，会短，当然是短。
没有像那个没有很好
OK， 他们，对啊，他们就是为了要做一件事情，就硬做就做出来了。OK， 哎，如果你们全部晚上一起读书啊，我就会来。OK， 然后你们再告诉我在哪里。啊？什么叫不看？待什么？一起啊，一起来。OK， 啊？我不懂，你们讨论一下，等一下，来讨论一下。
我不懂，对，他们都在问讨论的，
怎么嘞？
让我有些东西我这种确实，每一个声我都没有说，因为我啊，
Okay, let's look at this theorem here. So this theorem here says that if you start with a connected subspace, okay, A, and then you try and fill it in the limit point. Okay, fill it in, fill halfway, fill it all. Okay, fill it all. Okay, no matter how many points you fill, this set will remain connected. Okay. This theorem actually is quite convenient. It's quite convenient. For example, let's say if you take an open ball, okay, open ball which is connected. Okay, if you take an open ball here. Okay, so what is A bar? 来考一下 what is A bar here? What is the A bar of this? What is A bar? 什么 ？Ask Ivan. Ivan, what is A bar here? Sorry? Yeah, what's the closure of A in this case? Union with what? 很重要哦。limit point 也是 boundary point. Okay, so in this case here, what do you get? 你拿到什么？如果你把圈加进去啊 ，good. Okay, so you get a closed point. Okay, but the theorem says that if you are anything in between these two, it's still connected. A bar also connected, obviously. But what's everything in between? Can you imagine or not? Can you imagine? Yes. Okay, 就像你的月亮这样啊，可能只有半月吧，或者正月。Okay, so maybe you get partial. Okay, partial limit point still connected. Yeah, does it make sense? If you look at the picture. Maybe when you look at this picture, right? Will you immediately think about path connectedness?
when I say about connected, would you 会吗？不会，你直接是用 open set 来想，哇，厉害，对，很好。Okay, later we'll talk about path-connectedness. Okay, so should we prove these? We prove this. You want to see this proof? 要看吗？谁想看？你不想看？有人想看吗？赵正想看。Okay, let's prove this. Okay, again, 你看 you show something is connected 了。Okay, what can we do here? For the sake of contradiction, suppose that we can make a separation of B. That U intercept B is right this one. And this one. Open disjoint. Non-empty. Will be. Okay. So again, so B contains A, right? Okay, B contains A, and then A is a subspace. So meaning what? This connected subspace here must live entirely in U or in V. Okay, so without law of generality, let's assume that A live in U. Okay, so remember, we want to show that B is connected, so should get some contradiction here. But not that. We have A bar living inside U bar also. Okay, if you add the closure, okay, on both sides. In this case here, what can you see? Okay, let's look at, in particular, let's look at U bar intercept V. Okay, so what's this here, U bar intercept V? So basically it's U union with all the limit point of U. Intercept V. Good. Okay, but this intersection you can do distributivity, right? Okay, so you get U intercept V union with all the limit point. Okay, intercept V. Okay, but in this case here, what can you see? Why is it empty? U and V is empty. How about the other side? The definition before, what does the definition before say? Wouldn't be on the other side. That is the characterization of a connected subspace. Okay, so your limit point on one set wouldn't contain in the other set also. Okay, this is the characterization of a connected subspace. Okay, so both of them are empty. Okay, but what does this mean? But at the same time, you also have B live inside A bar, also live inside U bar here. Okay, in this case, says what? The large thing, the big thing U bar already intercept V is empty. This shows that B also intercept V is empty. But how do we build our V? Our V is a separation of B, which is not empty. But just now you prove that B intercepts with V is empty. Okay. Does it make sense or not? You have a larger set that intercept V is empty. So the smaller set contained in U bar surely much away from V. Okay, if I like, we can draw this out. So let's say this is a U bar. And then we got a V on one side. Okay, B is living inside here. Okay, so obviously the intersection is empty. Okay. Okay. All right. Let's see. What time is it? 4:17. Good, good. Let's continue. So next theorem. Actually, a finite Cartesian product of connected spaces is connected. Okay. With product topology, yeah, right. Yes, with product topology. Almost always, when we refer to a product space, here should be product. Okay. So what's the proof idea here? So let's just talk about two Cartesian product case. Okay, so let's just talk about look at x cross y. Okay, because you can do induction. Okay, if it works for x cross y. Can you think of how to prove these? So how do you think about product set here? How do you think about product set here? You got x on one direction, right? Okay, y on the other direction, right? Okay, but what is x cross y? So you can imagine at every point x, you put a y there. Sorry? What? Sure. So you got a lot of y here. Okay. Then we want to show that this whole space along horizontal line is connected. Along vertical lines. Obviously, I make things easy here. I draw the topological spaces like your R2 and that. But in general, it's like this classroom product with the other classroom. Okay. If classroom is a topological space. So, any idea how to show this? Any idea how to show this? What's the basis I'm looking here? So for example, like UI cross U2 like that. Two open set in XY. So how do you know that those open set are connected? You have to start with connected open set. Because open set could be disconnected, right?
Stop.
Mm-hmm.
Some X, I include all elements in Y.
Okay, so maybe you look at one line like this. So let's look at one line. So here is X. Here is X cross Y. Okay. Mm-hmm. No. You start with Y is connected.
Oh, yeah.
The point is, do you know that this line is connected? Why? And then, so this is the whole line, right? So this whole line is connected because this line is homeomorphic to Y. It's homeomorphic. So you can build a homeomorphism here. Right? Can you build a homomorphism here? You just send X comma Y to Y. It's a homeomorphism. And then you can do this for all X's.
X cross Y or some Y to X.
From some Y to X. Okay, so what do you mean by that? How do you do that?
The X cross that containing.
Okay, so you want to show that all the horizontal line also continuous. Okay, use the same tactic here. Okay, then how do you show that the union of all these things are connected? S. Huh? Which one?
No.
Hmm?
think X cross small y.
Oh, sorry. X cross y. Okay. And then, yeah. So the first thing is maybe you can show that this T shape is continuous, sorry, connected. This T shape is connected or not? Huh? Why? Just now how we connect two connected subspace. Yes. What's the common point here? X1. Okay, actually you can prove that all the T shape here, EX, so all the T shape here, EX should be connected. Huh? Sorry, what's the intersection?
X cross small y and small x cross y.
What are you trying to say? What are you trying to say? Their intersection is this XY point here. Yeah. So the union of them is a connected set. It's connected. Okay. But what? Yes, XY can be any point. So basically, X cross Y, right, is actually union of all these XY. But why? Oh, okay. Sorry. I'm not sure what you are referring to. Okay. Yeah. But our S cross Y is just union of these T shape, right? Okay. But all these T shape also have intersection. If you think about it, actually all these T shape has intersection. How do you mean? How to write them down? Let me think. How to write them down? How to write them down? That's like intersection. So how to say about this? So all the T shape must intersect with this T shape. Does it make sense? Does it make sense? All the T shape must intersect at some point with this T shape here, no matter how you draw. Okay, line, vertical line or horizontal line might miss some intersection, but T shape you cannot miss. Okay, make sense? Let me draw the ultimate T shape here. So this is the ultimate T shape. Everyone should intersect with this T shape. Every T shape, I mean, every other T shape. Okay, does it make sense? Hey, this is how people do the sewing, you know. 我去织你的那个布，或者织你的那个手工的那个盆啊，手工艺，这是人家怎么去织的，是交叉。Then you form a connected, connected space. OK， 这样你东西放进去才不会掉出来。OK 了 ？Does it make sense? OK, I write down the inverse inside the notes, but I just draw it here for you to understand. Okay. I'll give you one example. Something is not connected. Okay, so look at here. The key point here is I assume that a finite Cartesian product of connected space is connected. Okay, you can ask the question, can I go beyond finite Cartesian product or not? I go beyond that. Okay, so one counter example is infinite Cartesian product of connected space might not be connected. Okay, right. Hey, just now Eric asked about product or box, right? In finite Cartesian product, we don't really care, right? Because they are the same. Okay. So in this case here, find infinite here, I need to tell you what kind of product I want to use here. So let's take this R omega. So R omega here referring you take product countably many, okay, in the box topology. Okay, the claim is I can find a separation of this. This separation is very analytic. Okay, so how do I separate this? So I will separate it as a bounded sequence and unbounded sequence. Okay. Bounded sequence and unbounded sequence. Everyone know what is bounded sequence and unbounded sequence? So bounded sequence meaning all the terms are bounded by some number. So if you cannot find this number, then the sequence is unbounded. Okay. All right. What should we prove here? We need to prove that these two sets are disjoint, non-empty, and open. Okay, disjoint, non-empty, and open. I mean, disjoint is quite obvious now. You cannot be bounded and unbounded at the same time, right? Okay. Non-empty, I think you can show it also. You can go and find your. I mean, okay lah. Let's give an example. What's the bounded sequence here? It's in bounded sequence. Bounded sequence. 有人要救吗？终于就救他。什么是 bounded sequence? There's a number that bound from the top and bottom on both sides. On at every term. 每一个 term 都是 bounded 的。有一个号码可以 bound 完全部 term。什么？什么 sequence 是 bounded 的？很简单的。infinite sequence 对 ，infinite sequence 这个是 infinite sequence， 但是你要选什么 term 放在里面？很简单的，不要想这样远。什么？全部？给我一个，我不要全部，我要一个。sin x 是什么意思？sin yeah sure I mean yeah if we yeah bounded above by 1 bounded below by -1 but 还有更简单的嘛，对不对 ？You just take the constant sequence 哦。Okay unbounded 呢？yeah 1 2 3 there's no one number that can bound all the term。如果你选5，我还有100给你；你选100，我还有100万给你。Okay E over N what do you mean? 1 over 2 1 over 3 Is it bounded? Why is it bounded? Bounded by what? Yeah, not series. Yeah, don't confuse. 什么？谁不 bounded？ bound。他讲 series， 那个是 harmonic series， so it's not bounded. This is bounded. Why is it bounded? Bounded by what? Bounded below by 0, bounded above by 1. Yeah. Every term is bounded below by 0. 怎么还在这里 ？Sorry 啊，因为刚才你们在这边问，顺手写下去。Okay. So why is it open then? Oh, why is it open then? Okay, so how do you show that it's open? The two set in the union is showing empty. Okay, so why is it open? Open meaning what? So you need to ask about the metric here or the topology here. Basically, it's just a box topology, right? So yeah, it's a bunch of open interval product together. Okay, so if I gave you a bounded sequence or an unbounded sequence, how's the ball looks like? So if you take any sequence inside your R omega, okay, the open set looks something like this. Let's say we take a radius 1. Okay, but you think about it, if you are just a bit further from your bounded sequence or unbounded sequence, does it change your boundedness or unboundedness? It shouldn't change, right? You just add a finite distance to it. Okay, if it's bounded, every term already bounded, and then you slightly increase it by 1, slightly decrease it by 1. It's still bounded. But if you are unbounded, you slightly increase by 1, slightly decrease by 1. Still unbounded. Okay. Okay, so this open set should consist entirely of bounded sequence if A hat is bounded and of unbounded sequence if A hat is unbounded. Okay, okay, does it make sense? Okay, but second example is if you consider R omega in the product topology, right? It is actually connected. Okay, I think I don't want to do this in class. Maybe you can study about it. Okay, so second is if you consider R omega in the product topology, it's actually connected. Okay. Okay, we'll move on to path-connectedness now. To path-connectedness. Well, good. Before we do path-connectedness, right, I should tell you what is a path is. Okay. So, what is a path? Okay, so given topological space, X to T, and we will consider the closed interval 0 to 1 with the Euclidean topology. So for AB in X, okay, a path from A to B, from A, B in X, what is it? It's actually a continuous function. Okay, continuous function from 0, 1 to X, such that, okay, the starting point F0 is A, ending point f1 is b. Okay. So a path is a continuous function. Okay. So when you walk, right, when you walk in the classroom, right, actually what's the continuous function here? What's the continuous function here? Times from times to space. From time to space. Okay. So you are a function. 你是一个 continuous function. Because when the time moves, you create a path. So you are continuous. So but continuous function says what? The open set in X, the pre-image must be open. Okay. All right. So do I have example here? Okay. I get an example here. So let's say I got this time interval here 0 to 1. Okay. I got a function. Okay, what's the function here? Maybe I send this point to this point to the other point, and then that point to that point, and then something like this. Okay, and then I build out the path. Or maybe I build path like this, and then I join them together. Because a lot too many points, right? So you might think that they are joined together. Okay. But is this path continuous or not? Maybe I exaggerate a bit. Oh, this one go there. This one go there. Is this a path? Is this a path or not? Can I simply send here? 哇，很乱哦！你看这个人，这一秒在这边，另外一个秒又在那边飞来飞去，这个整个人就很不 continuous。啊 It's not okay. It's not when you think about the epsilon delta point of view. The nearby point should stay with the nearby point image. Should come from the nearby pre-image. Okay, so you cannot simply jump. So this is about continuity. Okay, it's not about open pre-image is open, but it's also about the local point around local point how you map. Okay, you cannot simply cross it. Okay, so continuous is really important here. I want to stress here. Okay, so make sure is continuous. Okay, definition here. Okay, so we said that a topological space xt is half connected if for every AB in X there exists a path in X from A to B. So meaning what? For every 2 points in this space, you should be able to find continuous function, okay, from the closed 0, 1 interval into X. Well, maybe give a very easy example here. Just now I missed it. So let's say if your point A equals to B, right? Okay, what's the path you can take? Huh? Fx equals to A. Okay, you can take this path here. This is a constant path. Constant path is very continuous, right? Okay, so you can take a constant path. Okay, which somehow we call a constant What do we call it? We suddenly cannot recall. Constant loop. Constant loop. Yeah, constant loop. Because you come back to the same point. Okay, so if your ending point and starting point is the same, sometimes we call it a loop. Okay, if A and B is the same, then we call it a loop. So if A equals to B, then the path is a loop. Okay. Because you're coming back loop. You learn Python, right? All of you. You learn for loop. What's for loop? What? What is for loop? You want to know what for loop is? What's for loop? Okay. 跳你下面的 algorithm， 还可以要跳回来吗？它是个 loop 吗？再 loop 多一次，你一定要回来那个 condition， 然后再跑一次，它就一直跑，一直从头，一直从头。Then you must come back. Okay, the starting point and point. Okay. Right. So our first theorem we're gonna establish here is if the topological space is path connected, then it is connected. Okay, let's do this. So again, how do we start? Suppose X is not connected. Suppose X is not connected, then there exists U and V such that we can write it as a union of U and V for non-empty disjoint open UV. Okay. Right. What's wrong with these? What's wrong with these? Since U and V are non-empty, this means that there are 2 points inside each U and V here. Because it's path connected, right? Path connected says what? So you got X, okay? You split it into U and V, okay? And then you go inside U and V here, find 2 points, U and V. But this topological space is connected, meaning what? I can find a path that connect them. Okay, so let F from the interval 0 to 1 to X be path in X connecting U and V. Okay. Right. So what's wrong with this? Anything wrong? Anything wrong? Anything wrong here? What can you do here? What can you do here? Can you separate someone or not? Can you separate the image of this path or not? How? Then look at this picture. Look at this picture. Look at this picture. Not drawing for fun one. Can you separate this? And how to separate? Take this image, intersect with U, and union with V. Wait, what am I doing? Intersect with U, and then intersect with V. Okay. Is this a separation or not? Non-empty, good. Open, because it's a subspace approach. Okay. Disjoint, why disjoint? U and V already disjoint. Can this happen or not? Why not? Why not? If not, that means this set must be connected. Then you need to argue why this set is connected. This is a continuous image of a connected set must be connected. Yeah. So contradicting the fact that continuous image of connected set is yeah. Okay, let's show you an example that why the other direction doesn't work. Any questions so far? Okay. Okay. So let's show you why the other direction doesn't work. That's mean if X is connected, does it imply that X must be half connected or not? Okay, unfortunately, no. Okay, unfortunately, no. Okay, so we will define this topology's sine curve. So let me introduce you to topology's sine curve. Not sin curve 啊，很有罪啊这条 curve，有罪啊这条 curve。Connected but not half connected. So what's this sine curve here? So this sine curve actually is closure of some curve. Okay. So what's the closure of this curve here? So the curve we consider here is a curve in R2 such that y equals to sine 1 over x. Okay, so let's draw this curve first. How to draw this first? This curve is a little bit tricky. Let me draw it to you. Okay, so what this curve does was, it is like the sine x actually, but when it get closer to the origin, it get folded pretty frequently. Okay, and then you will imagine that it never touches zero because 1 over x is not defined. Okay, so what's this limit point then? What's the limit point here? So if I imagine this more symmetrically, so it's bounded above by 1 and bounded below by -1. Okay, so actually you should imagine that there's a limit point. Its limit point lie on the line that is, this line is 0 cross -1. Okay. Right, so to show this is very interesting. How to show this? Basically, on this point, you need to build a ball around here. Once you build the point around here, you should show that there's some image of this curve meeting this curve, meeting the ball. Let me draw the ball. So if you make any ball around here, okay, you should find some intersection with this sine curve here. Okay. The point here is you cannot use open set to separate them. Okay? Yeah, you cannot use open set to separate them, but you cannot use a path to join to this line. This is kind of a miracle. 可以想象吗？ Can you imagine? 可以想象吗？ You cannot use open set to separate this set here. I mean, the way you want to separate it, I think, is this part here and this limit point. But but anyway, let me see. So if it's connected, then it's not path connected. But this is not path connected. Okay, so this is connected. Okay, you cannot have separation of open set, but you cannot find path to connect them also. Okay, because you might think that cannot separate cannot separate then 不能分开应该是有路去的，但是他告诉你没有路，没有路。 Okay, there's no path. Okay, this path will never reach this line one. Never. Not any point on this line also. 哪一个点都到不了。Okay, using path 啊，没有录到啊。Okay, 看到很近，但是一直走不到。Should we show this? I'm adding next time 了。OK， although 虽然我们分不开，但是我们也到不了。对，牛然之泥，哇哦，很浪漫耶。那这不是7月可以到的，也一天了，一天 ，OK。Okay. 100% on time. Okay. 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 Any question? Any question? Or any question for Victor?
Yes.
For Victor?
What is
Wait.
what is the question asked?
Wait.
Any sort of proposition?
Which?
Huh? Is important? Not very important. It's not first. Don't need to adjust strategy. Huh?
I looked out the proposition and then I can't use it because I prove it.
Oh, but I can't recall.
Okay.
At least I cannot recall. But the best thing you want to bring into the exam should be your definition and proposition, so that you don't need to remember. But if you want to copy some technique of proof, like the triangle encode, yeah, you can. Yeah, maybe it helps. Okay, because you could see that some proof pattern, right, keep repeating, right? Okay, maybe that technique you want to keep it. Until lecture 11, right? Yeah. Before hot dog space. Yeah, before hot dog space. Yeah, way before that. Way before that.
Okay.
Yeah, no continuous function, no need to worry. I hope not. Okay, so so if you have a meeting tonight, you can let me know. I can go and visit you. All right, good luck tomorrow, guys. Huh?